I noticed a lot of familiar names of people I haven't seen in years here. That's great. I also noticed a lot of names of people I've never met. So anyway, the idea behind the seminar, as you probably know, is to take a recent important paper in this area and then go through it in detail, more than just a summary of what you might hear in a colloquium or a seminar, and really learn about the details of the proofs and so on. And so we're starting out with Chromatic Quasisymmetric Functions by John Shareshian and Michelle Wax, which is about 5 years old now maybe, but it's become an increasingly influential paper. It's amazing how many people are working on some aspect of the problems they introduced. I think it's because it just connected to so many different areas, became kind of a unifying principle. So I'm Jim Haglund, and Anna Poon is the other co-organizer. If you have any questions, you can email me or her. And there will be recordings of these things available. And also I'll be posting the lecture notes on the seminar webpage. Everyone, by the way, has share screen capability. That becomes relevant. So any questions before we begin? If not, then I'm going to turn it over to John here. Take her away, John.
Well, thank you very much, Jim, and thanks so much to Anna and Jim for inviting us to speak on this. It's really gratifying to know that they're interested in this work, and that this is joint work, as was said, with Michelle, who's also going to be presenting some later lectures. We've been given a remarkable amount of time. We'll see if we're going to use it all or not. The plan is that I'll begin with definitions. I will show one theorem and proof in this lecture, along with some background, some conjectures, some discussion of motivation, and so on. And as we go on, we'll aim to prove more and more theorems and discuss later work by other people also.
Well, by the way, John, before we've already had an important question from Theodoros, namely, how do we ask questions?
I was just going to address that. So
I would like to try, at least initially, to run this more like a seminar where you kind of interrupt the speaker whenever you want to. And so verbally ask your question. And then if it's just too many people for that, then we'll go to chat, organized kind of stuff like we do in a conference. Is that okay with John?
Absolutely. That's what I was going to suggest. I'm happy to be interrupted.
Okay. Yeah, me too. Okay. So that's what we'll do.
Great. And if I don't hear you, just holler louder or something. Right. So so this joint work with Michelle, it appeared some years ago, as Jim said. There are two different kinds of motivation, and I am going to discuss one, and Michelle will discuss the other. What this goes back to, at least as I'm going to discuss it now, is some work of John Stembridge, some work of Richard Stanley, which I will begin with, and some joint work of Richard and John. And this led us to certain conjectures and results, trying to refine some conjectures and results of theirs. So I was told that what I should assume is that people know the basics of symmetric functions that you might find in chapter 7 of Stanley's Enumerative Combinatorics. Please don't hesitate to interrupt me if I start talking and it's something that you don't know and you think that just a small reminder would help. I am most happy to do that. So here I go. I want to talk first about Stanley's chromatic symmetric function. This was introduced in a paper, I believe, appeared in 1995. So the object is a graph, finite, loopless, simple. That doesn't really matter. There's at most one edge between any two vertices, right? And what we're going to be talking about are proper colorings. Kappa from V to the positive integers. So proper coloring just assigns a positive integer to each vertex such that if two vertices are joined by an edge, they get different colors. That's what proper means. All right. And so now Stanley's chromatic symmetric function, which will be denoted by this. So X, as usual, is an infinite set of pairwise commuting variables, right? This is the sum over all kappa in this K. So all proper colorings of X to the kappa. And what do I mean by X to the kappa, right? This is the product over all V in V, right? X sub color assigned to V. All right, so that's already a lot of noise, right? So let's just give some examples. So here's my graph, right? This is G. Here's a coloring kappa. I assign, I don't know, color 5 to this vertex, color 7 to this vertex, color 5 to this vertex here. This is a proper coloring because there are two edges, each of which have endpoints with different assignments, and X to the kappa, right, is just x5 squared, x7. Right. So this chromatic symmetric function, right, is just what you get by adding this over all proper colorings. Right. So this is an infinite homogeneous power series, right? In this case, right, the graph has 3 vertices. Every one of these x to the kappas is a monomial of degree 3. There's a whole bunch of them, right? And we add them, and the first observation is that this sum here is a symmetric function, because if I permute the colors, right, there's no action on the vertices of the graph. If I permute the colors of a proper coloring, right, I permute these numbers, I get another proper coloring, right? So this is a symmetric function. That's what I'm going to write for the algebra of symmetric functions. And let's continue with this example for this particular G. Right. Well, if I have 3 colors available, right, if I use 3 colors here, it doesn't matter in which order I use them. So I'm going to have 6 times M111. Right, M11 is the sum of all square free monomials of degree 3, right? And given 3 variables, there are 6 different ways I can assign the 3 colors here, right? Plus M21. Right, here I have 2 5s and a 7. There's only one way to assign 2 5s and a 7 to this graph, right? Because I put a 5 in the middle, then there's going to be an improperly colored edge. Right, so I want to remark that some straightforward computations with symmetric functions shows that this is, sorry, I have to peek, 3s11 plus s21, and it's also, I don't know if I believe that, 2, 3, 4, that's better, right? This is 3e3 plus e21. So these are Schur functions, the S's, and elementary symmetric functions, right? And so in particular, this is S positive and E positive. Now, that's not necessarily the case, that it's always going to be like that. Let me have a look here. Say G looks like this. right? One can calculate, if I haven't messed this one up. This is 24M1111, because it has to be, right? There again, n factorial ways, plus 6M21 plus M31. And this turns out not to be S positive or E positive. According to my calculations, these are also done in Stanley's paper. And if I made a clerical error.
John,
Go ahead, Jim.
you want M sub 2 1 squared?
Yes,
You need
thank
to
you.
have 4 colors.
Thank you very much. Yeah, this is always homogeneous. All right, then 8 S1, 2, 3, 4. And this is not S positive, and therefore it cannot be E positive. Because every E positive symmetric function is S positive. So this is some illustration, I think. I can't speak for Richard, but I think this is some illustration of Stanley's goals. Why is this interesting to start with? Well, the hope is that some aspect of the structure of the graph, right, is revealed when one attempts to expand this symmetric function in terms of the various well-understood bases. At least that's my interpretation of what's going on, and what you will see a lot of in Stanley's paper, right? And so, right, this is the idea, right? Expand G of X in terms of familiar bases. The ring of symmetric functions. What does this have to do with G? The usual graph theory of G. Right? This is the game. And so let me show you a sample theorem from Stanley along these lines. So let's write this chromatic symmetric function, right, in terms of the E basis. So this is a graph with n vertices, right, and say alpha lambda, that's a coefficient, E lambda, all right, so we've got to expand it in the elementary symmetric function basis. And then for any integer m, right, the sum over all partitions with m parts, alpha lambda, right, this here is nothing but, sorry, pen just stopped, number of acyclic orientations of G with exactly m sinks. Let me, rather than trying with this one here, let me just take a quick look here. Right? Well, this graph, most certainly every orientation is acyclic. That just means I'm going to put a direction on each edge. Acyclic means there's no directed cycle. This is the tree. There's no directed cycles. There are 4 acyclic orientations, right? And the claim of the theorem is that 3 of them have one sink, a vertex with no outgoing arrows, and 1 of them has 2 sinks, right? This is a partition with 2 parts, and the only one with 2 sinks is the one that points, both arrows point outward, right, from this vertex here. Right? So that's a sample theorem of Stanley's. I should remark, right, I would like to remark this, although it will not have much to do with what we're doing. This contains more information than the chromatic polynomial. Right, so the chromatic polynomial is known to be a polynomial, and it's a polynomial when you plug in an integer. It tells you the number of proper colorings. You plug in an integer n, it tells you the number of proper colorings in which the only colors that are allowed to you are the colors 1 through n, right? And the reason for that is, well, it contains at least as much information, because if I substitute 1 for the first n variables and 0 for the rest of them, then I'm counting proper colorings. This is not so hard to see. So this means that anything that the chromatic polynomial can tell you, the chromatic symmetric function can tell you. On the other hand, any two trees on the same number of vertices have the same chromatic polynomial, and it's an open question whether there exist non-isomorphic trees with the same chromatic symmetric function. Okay, so this chromatic symmetric function has gotten a reasonable amount of attention, right? A good amount of attention. In fact, like many of Stanley's ideas, they accessible yet getting to some very deep point about combinatorial objects. And so there's been a lot of work on this. What Michelle and I introduced was a refinement, this chromatic quasi-symmetric function.
John?
Go ahead.
Now in this polynomial, if you replace the x's with -1, what happens?
I do not know. So you would like to replace, say, finitely many of the x's with -1s?
Right. Just like you
no
did
idea.
with 1, yeah.
Maybe somebody else does.
Well, it's homogeneous, so wouldn't the 1 just come out, the -1?
Yeah, I think this is, oh, sorry, this is in fact correct, right? You would have to replace every other one, say, with a -1 or something like that, right? You get something. Yeah, I don't know what happens. Right, so you want to take, say, a specialization, a non-stable specialization where you put in q's and then substitute q as -1, put in powers of q, substitute q as -1. I do not know.
Thank you.
Maybe replace like the kth power sum by -1 for all k. That's a more common kind of thing.
Well, the power sum expansion is known, right? There are combinatorial formulas for the power sum expansion from which one should be able to, right, derive, right, what you get from that. I don't know what it is. Anything else, or should I move forward?
Thank you. Sorry for the interruption.
Oh, then please, that was, you shouldn't be sorry at all. Sorry, I don't know the answer. So what's chromatic quasi-symmetric function? So I should say this is the right name for it, but in the end, we're going to be talking about symmetric functions. We're going to be talking about graded symmetric functions, or if you prefer, either polynomials with symmetric coefficients or symmetric functions with polynomial coefficients. But these are quasi-symmetric functions until we restrict what class of graph we're talking about. So now we're going to label the vertices. So our graphs are finite. And as always, I'll write that brackets n for the set of integers 1 through n. Right now, the key point of this is that both the vertex set and the color set are ordered, right? With the usual order on integers. 1 is less than 2 is less than 3, and so on. So you have an ordered vertex set and an ordered color set, totally ordered. And what you know is that any two vertices in a proper coloring that are connected by an edge get different colors, right? And so this edge here gets two colors, and both the colors and the vertices are ordered. And you could ask whether these edges are ordered, if you like, as they should be, or in the opposite direction as they should be, right? So we take some coloring. Right? The G is fixed, right? This V is a vertex set. So we take some proper coloring of G and we define the ascent number. Kappa, this is nothing but the number of edges, say I, J in E, such that I is less than J and kappa of I is less than kappa of J. All right. So we have two vertices, one is less than the other in the usual order. They get different colors for sure. And so either the order of the coloring respects the order of the vertices or it doesn't. I'm going to count the so-called good ones. The theory doesn't change at all if you count the descents, right? And now what we're going to define, right, is xg, and we still have our x variables. We have one new variable t, right? And this is by definition the sum again over all proper colorings, right? T to the ascent number times x to the kappa. Okay. So this is some kind of refinement. When t is 1, this is just Stanley's chromatic symmetric function, right? And again, I just want to illustrate with some examples, right? So now I'm going to label my vertex set. 1, 2, 3, that's G, sorry. And now let's say kappa, I don't know, is 575, which I think it was before, right? Now this is kappa here, and ascent number is 1, right? Because this edge here is colored in the right order. 1 is less than 2, 5 is less than 7. This edge here doesn't give an ascent. 2 is less than 3, 7 is bigger than 5. So here from this we get t x5 squared x7, right? And so in fact, let's take a look. Let's compute for this particular G the entire chromatic quasi-symmetric function. And what I want to say, let me just write it out and I'll explain. This is 1 plus 4t plus t squared and 111, right, plus tm2, 1. Okay, why is this true? So first, let's look at this. Well, this is just saying the only way, this means I'm using one color twice and another color once. Well, if I'm going to use one color twice, it goes here and here. And now it doesn't matter if the bigger number is in the middle or the smaller number is in the middle, right? If the bigger number is in the middle, you have an ascent here and none here. If the smaller number is in the middle, you have an ascent here and none here, right? So however you use two colors once, one color twice and one once, you're going to get one ascent, just like here. Right? Didn't matter if I go 757. So you see t times m21. What's this? So, you know, if you're familiar with various things in enumerative combinatorics, this is the Eulerian polynomial. Why is that true? Well, what I'm going to do here, I write three different numbers up here, right? So basically, I'm writing a permutation of some set of size 3, right, up here. And what I'm counting are just ascents in the permutation, and that's the same as counting descents in the permutation. Right, and this is the descent counting or ascent counting generating function for S3, the Eulerian polynomial. Right, and now I want to, right now I'm sort of writing it as a symmetric function with polynomial coefficients, but when I want to write it in terms of S's and E's, I'd like to rewrite it as a polynomial with symmetric function coefficients. This is S3 plus T times 2S11 plus S21 plus, sorry, this is S111. plus t squared S111. And this is the same thing as E3 plus t times E3 plus E21 is 4 plus t squared E3. So this looks very promising because in fact this turned out to be symmetric, S positive and E positive, right? In the sense that the coefficient of the constant coefficient, the linear coefficient, and the quadratic coefficient are all S positive and E positive symmetric functions. Right? And
Did you miss out a 2, John?
do which one? Let's see.
2 E3 or no?
So I think E21 is a
2 E3.
three-dimensional representation, right? And E3 is a one-dimensional, so I get a 4 here. This always confuses me, but I think here I get a 2. This E21 is one of these and this one.
Oh, yeah.
Right. Okay. Yeah, I think I'm fine. Right. The key thing to understand here is 1, 4, 1. Right, and it's here in both places. Okay. So we shouldn't get too happy here, because there are 2 unpleasant caveats, right? So what I should say is there's no reason you should believe this is symmetric in the sense up here, because why should it be, right? This t messes everything up. And all I have to do to mess it up, right, is just change the labels on the graph. There's no reason to believe that when I change the labels on the graph, this is going to stay the same. And in fact, it doesn't, all right? I will not. This is my calculation. I think it's right. So it's close to symmetric, but that's again just luck because we're small. Right. So if I have 3 colors, well, now I'm asking, right, an ascent means that, well, again, on this edge, an ascent is an ascent, but on this edge, an ascent is a descent. Right. And so this is what you get. So that's not so terrible. It's symmetric, but in fact, you don't have a symmetric function. And this is, I think, reasonably clear. I'll explain it after I write. Looks like this, right? Because now I'm going to put 2 numbers here, right? I'm going to put the same number here and here. I'm going to put another number in the middle. If I've put the smaller number in the middle, then both edges are ascents. If I put the larger number in the middle, then neither edge gives an ascent. And so I see this. This is not a symmetric function. This is a quasi-symmetric function, right? This is, well, I guess, let me write Q for quasi-symmetric functions with coefficients in the polynomial ring, or if you prefer, polynomials with coefficients in the ring of quasi-symmetric functions. Right, so that's some weird Q that I write for the ring of quasi-symmetric functions. So you might not remember what's a quasi-symmetric function. A symmetric function, right? Any 2 monomials with the same multiset of exponents have the same coefficient. That's what it means to be symmetric, right? I take 2 monomials with the same multiset of exponents. They must have the same coefficient. To be quasi-symmetric, all you need is that any 2 monomials with the same sequence of exponents, this is 2 and 1, get the same coefficient. This is 1 and 2, and 1, 2 is different than 2, 1 in this setting. This is a quasi-symmetric function, but it's not symmetric. So this is bad news. There's other bad news, which says that in fact, the chromatic, whatever you want to call it, function is not an isomorphism invariant of the graph. It's maybe an isomorphism invariant of the labeled graph. This is completely unsurprising and looks unpleasant, but here we go. Here's something nice that happened up here, right? That's what's going on, right? Well, there are 2 ways to go. You could look at Stanley's symmetric function, and every symmetric function is quasi-symmetric. And in fact, there's some very nice work of Tim Chow, right, that talks about expanding the chromatic symmetric function in terms of one of the standard bases for the ring of quasi-symmetric functions. And you could go that way, and we do in the paper, and eventually we'll get to that. But our goal is to understand where this is coming from, right? Why did this work so nicely? You shouldn't expect this. If you close your eyes and pick a graph, you're not even going to get something as nice as this. You're going to get some mess of a quasi-symmetric function, right? So the way we were looking at it is in some way to explain this, and we have a good sufficient condition. I don't think there's a really good necessary and sufficient condition. And here I just need more definitions. Let me just pause for a second and ask if anyone wants to speak up now. Okay, so what's a natural unit interval order? So there are lots of ways you can define this, and I'll return and redefine it as I need, but I want to make a definition that allows us to move forward as quickly as possible. So, in fact, let me call this graph, natural unit interval graph, right? Because we're going to be talking about graphs, but I'll also talk about orders, right? So what we're going to start with is a so-called Hessenberg vector. So I'm using M now in a different way than I was before. So I have a list of n positive integers, and I want to call this a Hessenberg vector. If two things hold, this is a weakly increasing sequence. And two, I is less than or equal to mi is less than or equal to n for all I. Okay, so it's a weakly increasing sequence of, in fact, I should maybe have put here n to the n, right? And the ith entry is at least I. So here's one, like this, right? And now we get a post set on the set 1 through n, where I is less than, let me give this some kind of symbol like less than an R post set. J, if M sub I is strictly less than J. Okay, that's a post set for this particular Hessenberg vector here, right? This says that 1 is less than 4 and 5, right? To be bigger than 1 in this post set, you have to be bigger than 3 in the usual order, right? So 1 sits below 4 and 5, as does 2, and 3 sits below 5. Okay. And there's an incomparability graph. Let me just...
John, before you proceed.
Sure.
Yeah. First, I think you can count, but do you know how many, for a fixed n, how many Hessenberg vectors there are?
Yeah, there's a Catalan number because these are in bijection with dig paths, and we're going to talk about this later. But since you asked, right, let's see, dot, 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 0, 0, right? I put 3 dots in the first column, 3 dots in the second column, 4 dots in the third column. Certainly my right, these pictures are in bijections with Hessenberg vectors, right, where a French style partition has been cut out of the lower left corner, and such pictures like this are in bijection with dig paths, right?
Right. Is there by any chance any reason why you picked the Hessenberg vector? Because there is a Hessenberg matrix.
Yes, and in fact, this is how to say, this is so you are prescient, and let me put the pen down because we can see what's coming. The Hessenberg matrix is exactly when we would see 2, 3, 4, 5, 5. You would see, except for the last entry, which has to be n, according to the rules, if the ith entry is I plus 1, then what you see is, well, you have this upper triangular matrix plus what's just below the diagonal. And these ideas were introduced in applied math by Demari and Shaman, as we will discuss. And the idea is you can associate to this picture and a generic matrix, a certain kind of variety, and the geometry of that variety controls the efficiency of an algorithm that will take an arbitrary matrix and conjugate it into this form, right? And so in particular, right, in numerical linear algebra, when they're trying to do certain kinds of numerical linear algebra, you might imagine that the idea is to triangularize, right? Then you can quickly read off the determinant. But for certain activities in numerical linear algebra, as I learned way back in my first or minus first year of graduate school, it's better just to put in Hessenberg form. You can go faster and still obtain useful information in some settings. Right. And so the question is, how quickly can you put a matrix into Hessenberg form, which is like almost triangular? And it turns out that associated is Hessenberg variety, and I'll be discussing the Hessenberg vector is some variety. And the Demari and Shaman investigated, right, what that has to do, the topology actually of that variety has to do with how hard it is to move things into Hessenberg form. Right. So that's a very appropriate question. And so this is just some kind of generalization of Hessenberg form. Right? If the ith entry is I for all i's, this picture would just be upper triangular. You have zeros below the diagonal. So it's just some kind of generalization. Okay.
Thank you.
And thank you. So, all right. Yeah, there's a Catalan number. We have this post set, and now I want to make a graph because we're talking about graph colorings, and this will be the incomparability graph, right, of this post set. So two vertices are connected by an edge if they're incomparable. And if you go back and stare at this Hessenberg vector, that tells you exactly what to do. Right, this the natural linear order is a linear extension of this post set, so I can kind of write these 1 through 5 from left to right. And this 3 tells me that 1 is not less than 2 or 3, and never in this post set is a bigger number less than a smaller number. So I know that 1 is comparable to 2 and 3, 2 is comparable to 3, incomparable and incomparable like that. Right, so I don't need this post set if I want to make the graph. I just stare at this 3. It tells me to draw edges from 1 to 2 and 1 to 3. I stare at this 3. It tells me draw an edge from 2 to 3, but not to 4 because 4 is too big. This tells me to draw an edge from 3 to 4. This tells me to draw an edge from 4 to 5. This information is always extraneous here. All right, so sooner or later, there should be a theorem and a proof, right? And now's the appropriate time. I mean, I hope to give more theorems and more proofs, but these are all the definitions that we're going to need for now, right? And there should be a theorem and a proof. And let me remark, right, if we look at the graph we had before, I just want to draw this one here, we see this graph, right? This is exactly the graph. This just tells me draw an edge from 1 to 2, draw an edge from 2 to 3, don't draw an edge from 1 to 3. This was exactly the graph that had the nice quasi-symmetric function, right? This, according to Teddy's question, this would be exactly a matrix in Hessenberg form, a 3 by 3 matrix in Hessenberg form. It would correspond to just having a 0 in the lower corner, right? And this was the one that had the symmetric quasi-symmetric function, and this is the theorem. All right. M is a Hessenberg vector. then this chromatic quasi-symmetric function is in fact symmetric. Okay. Right. So again, I can think of this two ways. It's a polynomial in T, right? Because they're at most, say, I don't know, inches to a sense or something like that. So it's not a full power series in T, it's a polynomial in T, right? And each coefficient is symmetric, or if you prefer, I can write it in terms of any one of my symmetric function bases, but instead of the coefficients being integers, they're polynomials, right? So this I'm going to try and prove, right? Hopefully successfully. The proof, the idea, right, is, I think, fairly clear, right? So let me write the idea, because there's a kind of minor subtlety here. We're going to show that this invariant under each transposition say XA gets exchanged with XA plus 1. Okay. So the subtlety, right, you might make a reasonable complaint that this doesn't prove anything because a symmetric function is invariant under every permutation of the variables, and certainly, right, these permutations of finite support, these transpositions can't generate the whole symmetric group on the variable set. But if you think about it, if you have a non-symmetric function, it means there exists two monomials with the same exponent multiset that have different coefficients, and you can map one of these to the other with a permutation of finite support. So in fact, the symmetric function is one that's invariant under all permutations with finite support, and these transpositions most certainly generate that group. Right, so you don't have to worry about, you know, that you need all permutations, right? And so this is sufficient. So we need some lemma, right? So the idea is that we have some proper coloring, right? And it's some of it, we use color A on some vertices, we use color A plus 1 on some other vertices, and we use, you know, a whole bunch of other colors elsewhere. And what we would like to do in some way is exchange the A's and A plus 1s, right? When we exchange the A's and A plus 1s, certainly we still have a proper coloring, right? But what could go wrong? Well, there's several things that can go wrong. There could be more A's and A plus 1s and so on, right? And we most certainly could be messing around with the ascent number when we start changing the A's and A plus 1s, right? And how can we be messing around with the A's and A plus 1s? Well, if we have some number A, some vertex with color A, and its neighbors don't have color A plus 1, and we change this A to an A plus 1, that doesn't change anything, right? We're still going to have a proper coloring, and the ascent number is going to stay the same because the other colors are neither A nor A plus 1, and therefore, if they're less than A, they're less than A plus 1, and vice versa. So if we start messing around, right, with vertices by just changing the color from A to A plus 1, whose neighbors, right, don't involve A and A plus 1, there's no trouble. The trouble arises with edges that have one vertex colored A and the other vertex colored A plus 1. That's what's going to cause us trouble. And we just need some method to exchange things and not mess up the ascent number. We're just going to switch the A's and A plus 1s because that's what we have to do, right? And we would like to do so in a way that doesn't change the ascent number. We're going to switch some of them, right? So this tells us, it behooves us to look at the subgraph induced on vertices with colors A and A plus 1. Right. So here's a lemma. Right. So we're given one of these Hessenberg graphs. That's what I want to call them, right? This is a Hessenberg graph. And some proper coloring. We have some proper coloring. And we're given a particular color. Right? Then we're going to define G. I'm going to get rid of the Hessenberg vector because I don't want too much notation. This depends, right? The graph G is fixed. Maybe I should just call this G. Graph G is fixed, right? Now we also fix this A, and now we're given one of these. So I imagine as G is fixed, this number A, which I'm going to exchange with A plus 1 is fixed, right? And now I'm given some proper coloring, right? So this really depends on kappa. That's varying, right? We're going to define this to be the subgraph of G induced on, I guess I could say it this way, kappa inverse of A, the set of vertices colored with A, union kappa inverse of A plus 1. Right? And the claim then, right, every connected component of this graph is a path, right? Say I1 less than, well, here's I2, Ij. J is just some number. So these are J vertices in the graph, right? There are edges like this, and this is the entire induced subgraph, and these vertices are appearing in increasing order. So let me show you an example. Right. Once we prove this, as I'll explain, once we have the proof of this in hand, the theorem is not very hard to prove, right? This claim will follow quickly. Okay. So let's take the following Hessenberg graph. So let's say M is 3, 3, 4, 5, 6, 6. So the graph looks like this. And let's say kappa looks like this. 5, 2, 6, 5, 6, 2. Right. Okay. Then G sub kappa 5 looks like this. 1, 3, 4, 5. It's a path. Right? These are the vertices labeled 5 and 6. I see the path 1, 3, 4, 5, and maybe G sub kappa 2. I'm looking at the vertices labeled 2 and 3, but there are no vertices labeled 2 and 3. So this is the disjoint union of two paths of length 1. Right? So this is the claim of the lemma. Right? This graph, if I just look at the vertices colored A and A plus 1 for any A, right? For all A's besides 2, 1, 2, 5, and 6, right? For all 1, 2, I guess, yeah, 1, 2, 5, and 6, it's empty, right? It's typically empty because there's infinitely many colors and finitely many of them get used. Right, but otherwise, right, it's just a disjoint union of paths. Okay, so this is what I want to prove. Right. As I said, the theorem will follow quickly. So the first observation is that G, what's it called? Kappa A is bipartite. Right, because, well, there's the vertices labeled A and the vertices labeled A plus 1, and those are both independent sets. and in particular, so contains no 3 cycle. All right, so in particular, if, what do I want to call these? X, Y, and Y, Z are in the edge set, then X, Z is not in the edge set. Right? There's no 3 cycle, there's no K3, if you like. So I want to look at this picture. What does this mean? Say I have a picture like this, right? I want to understand what can happen here, right? The goal, either X is less than Y is less than Z, or X is greater than Y is greater than Z, in the usual numbering. This is the usual numbering, okay? And so here, right, this is just a case analysis. I want to say, you know, you could assign this in a class, right? This is a just straightforward observation case analysis, right? So case 1, right, X is less than Y, right? What does it mean? Well, we have this edge XY, right? And what that means is that Y is at most M sub X, right? X, Y, and Z are numbers from 1 through N. They live in the Hessenberg graph, right? I have this edge X and Y. This means X and Y are incomparable. We know X is less than Y. If Y were bigger than M sub X, they'd be comparable in the post set, and therefore there would be no edge in the graph, right? Well, either, right? What do I want to say? Z is less than or equal to M sub Z less than X, or, right, X is less than or equal to M sub X is less than Z. This is because there's no edge XZ. That comes from this argument here, right? There's no edge XZ. This means X and Z are comparable in the post set, right? So either, right, MZ is less than X or MX is less than Z, depending which of X and Z is bigger, right? But this is impossible. Why is that? Right? Because it implies, right, that Y is greater than MZ. Right? So this, I mean, if you're not following, don't worry at all. You can do this on your own time. Right? This just implies Y is bigger than MZ, which we know is not true because there's an edge here. Right? And now, right, so X is less than Y is less than or equal to MX is less than Z. And we get X is less than Y is less than Z, right? Similar argument. I don't want to belabor this too much. That if X is bigger than Y is bigger than Z. Okay. All right. So now I want to look at any path. Given a path, say, I don't know, I1, I2, Ij, right? In this graph that we're talking about, right? Either I1 less than I2 less than dot dot. This path has to either come in ascending order or in descending order. right? This is just induction, but I have this path and I can just look at this piece of the path starting at each vertex, right? And once I know, say, if this is less than this is less than this, then I know this is less than this, and therefore this has to be less than the next one, and so on, right? So this is a direct consequence. Again, this is an elementary argument, right? And now G is a forest, right? Because I can't have a cycle. Every time I move along a path, this isn't an induced path, it's just a path, right? Not an induced path, any path. I have to have this, because as soon as I see one of these paths of length 3, I know I don't have this edge overarching, right? So this is any old path, and I have this either weakly increasing or weakly decreasing, so there can't be a cycle. I can't return. This ij can't be I1, right? And so G's a forest, and it remains to show, right, that every vertex in this is G kappa A, in G kappa A has degree less than 3. Right, I've got a forest. My goal was to show, let me just scroll back up, right? My goal was to show that I have a bunch of paths with these properties. So what I know so far is every path has this property. I just have to write it in the correct order. If it was descending, I just rewrite it in the other order. That's not a problem, right? And so every path looks like this. Every component is a tree, and so the remaining thing to show is that, you know, each of these trees is in fact a path, which just means show that no vertex has degree 3 or more. And now, right, I will just draw you a picture, W, X, Y, Z, like this. So now this is again not troublesome. It's completely elementary, right? I just look at this path. Right? And so, I mean, without loss of generality, X is less than W is less than Z, right? Because I can exchange X and Z here without any trouble. But now, X is less than W forces that W is also less than Y, right? And this is bad news. For Y, this path here, right? This path can't be ascending or descending because the smallest thing's in the middle, right? We know X is less than W. This path is ascending. This path ascends at this edge, so has to ascend always. And now this path can't ascend or descend because the smallest vertex is in the middle, right? And that's the end of the proof. Okay. All right, so we know the structure of a subgraph induced on those vertices that get consecutive colors. And now the last thing to do is to understand, to make some bijection. Oh, it's perfect. It's time for me to stop, right? But this I can write, I'm sorry. I can write in,
No worries. We started a little bit late, so if you have time.
Well, this is short. We have an involution, right? On K given A, right? Given a connected component, right? I1, 2, Ij is above. Do nothing, right? This is a component of G kappa A. Right? Do nothing if J is even. Right? Exchange colors I and j, sorry, a and a plus 1 if j is odd. Right, so I see something like this. These are coming in increasing order, a plus 1, right, a plus 1, a, right? And I just change the coloring. The graph is remaining the same. I want to change the coloring, right, in such a way that the number of a's and a plus 1s are exchanged, right, and that the number of ascents stays the same. A plus 1, a plus 1, a plus 1. And if you see, this contributes 2 ascents, and so does this. Whereas, right, what I don't want to do sorry. I don't want to do this because this contributes 2 ascents, but this contributes just 1. Right? So this is an involution on colorings that depends on the chosen number A. It's an involution on proper colorings, right? That in fact preserves the ascent number, right? And preserves the monomials. It does everything we want, right? So this is the proof of the theorem, and what it's telling us is it's going to be interesting to study chromatic quasi-symmetric functions of natural unit interval graphs, right? And as Teddy asked, there's something interesting going on. There's Catalan many natural unit interval graphs, and they're associated the Catalan many varieties, right? According to a conjecture of Michel's and myself, which was proved by Patrick Brosnan and Tim Chow. So let me stop, and we'll continue next time.
Okay. Well, let's thank our speaker. Very good. And John, in case you were wondering, that's the perfect amount of detail and background and all that. So
Great. So I will attempt to continue in this vein. Next time I'll talk about the Stanley-Stembridge conjecture, our refined conjecture, and hopefully get to the part where you relate this to Hessenberg varieties.
Okay. Great. So are there any questions before we stop?
Yeah, I have one. Great presentation. So are there any other families of graphs where this quasi-symmetric function is known to be symmetric, like these nice kind of local lemmas like you just proved?
Yes, and Michel will talk about this, and in fact, some, if you make a slight adjustment, there are beautiful results due to Michel's former student, Brittany Elsie, where you could think instead of thinking this as a graph, you think of it as a directed graph, where all the directed edges, right, go from lower number to higher number, right? And then an ascent is a coloring that respects the direction of the edges, right? And so you just direct all the edges one way, right? And now a theorem of Brittany says, in fact, you could have a directed cycle, right? And now you're going to count ascents, right? And that's actually going to be symmetric, right? Now you're asserting that 1 is less than 2, is less than 3, and so on, is less than n, which in fact is also less than 1, right? And yet you will get a symmetric function. So that's slightly different than we're saying here, but also regular cycles, you can get symmetric if my memory is correct. So this, what we have no idea, as far as I remember, about any good necessary conditions. And on the other hand, I mean, I would bet you everything I have in my wallet that if you close your eyes and pick a graph, it's not going to be symmetric.
Thank you.
If I didn't have a family, I'd bet you my house, but they live.
So, yeah, I know of only one example where with a labeled graph that is symmetric, and that's in addition to these unit interval graphs, natural unit interval, the cycle that where you label from 1 to n,
and
Still.
not to
not the directed.
not to cause any spoilers, but are there any potential connections between that cycle example and geometry, or
No, I don't know any. I don't know any connection. That would be nice to know. But so when you go to directed graphs, as John was saying, then there's a lot of examples that generalize the natural unit interval graph. But when you stick with the way John defined it, the labeled graphs, I only know of the cycle that has a symmetric chromatic quasi-symmetric function that's not a natural unit interval graph.
thanks, Michelle.
One of the problems that I view trying to connect those things with geometry is that the constant coefficient in this polynomial, right, is not 1. So you don't have some connected manifold, right? And so it would have to be like some local thing, right? There are H vectors. The Betty numbers of these manifolds are not H vectors of polytopes, but just imagine, right? You have these Hessenberg rise. Imagine they were just for fun, right? So then when you go to these cycles, you would need some local H vector or something because it doesn't start and end with 1. And so, it's kind of beyond me what to do geometrically there.
And anything like Poincare duality is just not going to.
So I think there's symmetry, but Michelle will correct me if I'm wrong.
Oh, okay.
That's right. You do get the same things you get from the connection with the variety. You get unimodality and symmetry, but we don't have a geometric explanation.
Maybe I have one other remark along these lines. It could be a sum of something geometrically interesting, right? Because besides the famous Stanley-Stembridge conjecture, there's the other Stanley-Stembridge conjecture, which says that these representations, or if you like, symmetric functions that arise in Stembridge's work on immanence, if you've read that, are in fact sums of chromatic symmetric functions. And if I get the time, I'll mention some work of Nate Lesnovich, who works with Martha Prekup and I, a graduate student here, who has some results towards the second Stanley-Stembridge conjecture, which hasn't gotten too much attention as opposed to the first one. So it's possible that it's a sum of something, some interesting things. So, a disjoint union of some nice manifolds, but I don't know.
Thank you.
Oh, I see that there's a question in the chat. Yeah, so I think Joseph is asking, are there any graphs where no labeling of the graph makes the chromatic quasi-symmetric function symmetric?
Okay, so I wouldn't bet my house on that one, but I still might bet my wallet that the answer is yes. Pick, reasonably large n, pick a random graph. My guess is that, now I'm guessing more, but I would guess. But Michelle might have a better guess.
I don't know.
Tom Foster now says he thinks the claw satisfies that.
That's almost, that's a good idea, which is likely to work. Yeah, that's a good idea. Again, I would guess that such graphs have asymptotic density 1, but I'm guessing.
So any other questions for John? Comments? No? Okay, so we'll stop here for today and we'll see you all on Thursday, hopefully. So long.
Thank you all very